Okay, let's dive in. We're tackling something pretty big today, an 80-year-old scientific mystery about our sun.
That's right. A really fundamental question about how it works.
And it seems it's finally been solved. Not just by, building a bigger telescope, but by figuring out something much trickier.
Finding a whisper in a roar, essentially.
Exactly. So this deep dive is all about that discovery. The first definitive observation of these tiny, continuous, twisting magnetic waves. They're called torsional Alfvén waves.
And they're happening in the sun's superheated outer atmosphere, the corona.
Yeah. And the sources show this was done using the most powerful solar telescope we have. So our mission today, we want to trace this long search, understand what these waves actually are, and really show you why finding them might just unlock one of the sun's biggest secrets.
And that secret, the core puzzle that's bugged solar physicists for, well, forever it feels like,
Yeah.
is just the fact that the sun's outside is way, way hotter than its surface.
Which just feels wrong, doesn't it? It defies basic intuition.
Completely. Think about it like this. You step away from a campfire, you expect it to get cooler, right?
Right.
But with the sun, visible surface, the photosphere, that's about 5,500 degrees Celsius. Pretty hot, but, relatively cool compared to what's next.
Okay.
Then you move just a bit outward into the corona, that beautiful halo you see during an eclipse.
Yeah, the shimmering part.
That skyrockets. We're talking several million degrees Celsius.
Wow.
And that massive jump, that's the famous coronal heating problem. How do you pump enough energy out there constantly to keep it at millions of degrees? Finding that mechanism has been, well, a kind of holy grail.
And the basic idea for how this could happen, the theory, it's actually almost as old as the problem itself. Our sources point back to Hannes Alfvén, a Nobel Prize winner who way back in 1942 first proposed these things called Alfvén waves.
Right. These magnetic ripples, essentially, that can travel through plasma, the superheated charged gas the sun's made of, and carry energy.
It was a brilliant idea, really ahead of its time.
And what's interesting is scientists weren't starting completely blind. They had seen other types of Alfvén waves before.
Okay, so they knew these waves existed in some form.
Yeah, but the ones they'd seen were bigger, more dramatic, usually linked to huge events like solar flares,
Yeah.
big explosions.
But they'll bangs.
Yeah, exactly. Like massive solar earthquakes, obvious, powerful, but they happen sporadically. They couldn't explain the constant, steady heating of the entire corona.
So they needed something smaller, something more like a continuous hum instead of the occasional boom.
Precisely. A steady, low-level mechanism constantly feeding energy into the atmosphere.
Okay, so they had the theory from the 40s. They'd seen the big waves. Why did it take until, well, now, basically, to actually find this continuous hum? What was the holdup?
Well, because the specific waves they were looking for, these torsional ones, are incredibly subtle, just really, really faint signals. And detecting them needed a whole new level of observational power.
And that brings us to the tech, right? The telescope.
Exactly. The Daniel K. Inouye Solar Telescope decased up on Haleakala in Hawaii.
Right, I've read about this. It's this massive international project. Took like 2 decades to plan and build.
It's a beast. The main mirror is 4 meters across.
4 meters? That sounds huge for a solar telescope.
It is. It's about 4 times larger than previous ones used for this kind of work.
So was it just about being bigger, collecting more light, or was it the instruments on the telescope?
Good question. It's really both. The huge mirror collects vastly more light, letting them see incredibly fine details on the sun, like features the size of Texas, basically.
Oh.
But like you said, you need the right instrument to actually analyze that light properly. And the key piece of hardware here was something called the cryogenic near-infrared spectropolarimeter.
Okay, let's maybe not try to say that too many times. The advanced coronal camera.
Yeah, let's go with that. It's incredibly sensitive to tiny shifts in how the plasma is moving. It allowed the team, led by Professor Richard Morton, to track the movement of iron atoms heated up to about 1.6 million degrees Celsius.
Just tracking individual atoms or groups of atoms that hot millions of miles away.
Yeah.
The precision is just staggering.
It really is.
But here's where, for me, it gets really interesting. Because even with this amazing telescope and this super sensitive camera, the data wasn't clean. It was still full of noise.
Oh, absolutely. The biggest challenge wasn't just seeing something, it was seeing the right thing.
Because the sun's atmosphere is just constantly shaking.
Exactly. Those magnetic loops stretching out from the sun, they're always swaying back and forth. These are dominated by what are called kink waves, big visible oscillations.
Okay, so kink waves are like the whole structure swaying.
Precisely. Imagine like a long rope tied to a pole. The magnetic field is the rope. A kink wave makes the whole rope whip back and forth. You can actually see this in videos of the corona. It's the dominant motion.
And that visible swaying was basically drowning out the signal they were looking for.
Completely masking it. Because the torsional Alfvén waves, the ones doing the heating, they don't cause that big sway. They cause an internal twisting motion, like twisting the rope around its own axis.
Okay, so one is side to side, the other is rotational.
Right. And you can't see that twisting visually, especially from Earth, and especially when the whole thing is already shaking violently side to side.
So how did they do it? If the main movement hid the crucial one, how did they isolate it? This sounds like the real breakthrough.
It absolutely was.
Yeah.
Professor Morton and his international team, they had to basically invent new ways to analyze the data, new algorithms. Their whole approach was about, as they put it, removing the swaying to find the twisting.
So filtering out the noise digitally.
Exactly. They had to mathematically subtract the effect of the known visible kink waves to see if anything else was left underneath.
And how did they measure that invisible twist? What was the signature?
This is the clever part. Since they couldn't see it directly, they used spectroscopy. They measured the light coming from those superheated iron atoms, looking for the Doppler effect.
Okay, Doppler effect. Like the sound of an ambulance siren changing pitch as it passes.
Precisely that principle, but with light. If something is moving towards you, its light waves get compressed, shifting towards the blue end of the spectrum. If it's moving away, the waves stretch out, shifting towards the red end.
Right, red shift and blue shift.
Exactly. So imagine that magnetic rope again. If it's twisting, the plasma on one side of the rope will constantly be rotating towards us,
Giving a blue shift.
while the plasma on the opposite side is simultaneously rotating away from us.
Giving a red shift.
Yeah.
On opposite sides of the same structure.
Yes, and that's what they found. Consistent opposite sign velocity signals, blue on one side, red on the other, right across these magnetic loops. That pattern is the smoking gun for torsional Alfvén waves, a continuous internal twisting.
Wow. So that's the definitive evidence.
That's the definitive evidence. And it validates the whole theoretical picture, the one proposed way back in the 1940s. This constant, subtle twisting is the likely mechanism pumping energy into the corona, heating it up to those crazy million-degree temperatures.
It confirms that Alfvén wave turbulence really does power the solar atmosphere. So, okay, mystery likely solved, which is huge for solar physics. But what does it mean for, us down here on Earth? Why should you, listening now, care about tiny magnetic twists millions of miles away?
Well, if we connect this to the bigger picture, it's actually massive for something really practical, space weather prediction.
Okay, solar storms, that kind of thing.
Exactly. That intense heat in the corona, driven by these waves, is what powers the solar wind. This constant stream of charged particles flows out from the sun and fills the entire solar system.
And that wind carries the sun's magnetic field with it.
Right, and when the sun has outbursts, those disturbances travel through the solar wind and can hit Earth's magnetic field.
Causing problems for satellites, GPS.
Power grids, communication systems, all our modern tech is vulnerable. So understanding the fundamental engine driving that wind these torsional waves is the first step towards actually predicting those potentially damaging events better.
And there's another connection too, right, with NASA's Parker Solar Probe.
Oh, absolutely. The sources point this out clearly. These Alfvén waves are strongly suspected to be the origin of something called magnetic switchbacks.
Switchbacks. What are those?
There are these bizarre, sudden reversals in the direction of the solar magnetic field that the Parker probe keeps flying through as it gets incredibly close to the sun.
So the probe is seeing these weird magnetic flips out in space.
And this discovery, these torsional waves near the sun's surface, provides a potential source mechanism for them. It suggests how that twisting energy might be released and propagated outwards, creating these structures far out in the solar wind.
So finding these waves doesn't just solve the heating problem. It could also explain data from our most advanced solar probe, tying together physics near the sun with phenomena way out in space.
Precisely. It links the theory, the ground-based observations, and the in-situ spacecraft measurements into one coherent picture. It's why this is such a landmark discovery.
And it really highlights the effort involved.
Yeah.
You said it was an international team?
Yeah, researchers from the UK, China, Belgium, the US, other places too. It took this global collaboration to pull together the telescope, the instruments, and the new analytical techniques. It was a huge undertaking on all fronts.
So where does the research go now? They've found the waves. is the job done.
Oh, not at all.
Yeah.
This is really just the beginning of a new phase. Now that they have definitive evidence that these waves exist, they can start probing how exactly they work.
Like how they deposit their energy, how the twisting actually heats the plasma.
Exactly. They can now test specific theoretical models about wave dissipation and turbulence against actual observations. It opens up a whole new avenue for studying the detailed physics of the corona.
Amazing. Decades of searching, and now they have the key.
Mm-hmm. And, this whole process, it raises a really interesting, broader question, I think. Well, consider that Professor Morton's team had to invent entirely new ways to filter out the obvious visible motion, the swaying, just to find the crucial underlying twisting motion.
Right, the signal was hidden by the noise.
So it makes you wonder what other important processes, what other fundamental physics, maybe not just on the sun, but in other complex systems like, I don't know, climate dynamics or even fluid dynamics or particle physics,
Uh-huh.
what else might currently be completely masked, just hidden from us, because we're only seeing the big, dominant, superficial motions, the things that are easy to see.
That's a fascinating thought, that maybe the biggest challenge sometimes isn't building a better instrument to see more, but developing the insight to filter differently, to look for the hidden signal within the data we already have.
Exactly. Sometimes the breakthrough isn't a bigger lens, it's a smarter filter.